All right, let's jump right in. Today, we're going to pull back the curtain on a really slick feature inside Cisco ACI called ARP Gleaning. It's one of those awesome mechanisms that just works quietly in the background, making the whole fabric smarter and way more efficient.
So let's start with a problem I'm pretty sure every network engineer has run into: the silent host. You know the one, it's plugged in, it's powered on, but it just hasn't sent out any traffic yet. So as far as the network is concerned, it's a ghost. The big question is, how does a smart fabric like ACI find this thing without just blasting traffic everywhere the old-fashioned way?
So here's our game plan. First, we're going to really define what this silent host problem is. Then, we'll introduce ARP Gleaning as ACI's solution. After that, we'll watch it in action, looking at a couple of key scenarios, inside an EPG and across them. And finally, and this is super important, we'll talk about when ARP Gleaning doesn't kick in.
Okay, section 1, the silent host problem. You know, in the real world, silence can be golden, but inside a high-performance network fabric, not so much.
It's pretty simple, really. When a host is silent, ACI has absolutely no record of it in its endpoint tables. So if another device tries to talk to it, the fabric just throws its hands up and says, "I don't know where to send this." Now, a traditional network might just flood that ARP request to every single port. But ACI is built for massive scale, and flooding is a huge performance killer. It just creates broadcast noise that chews up CPU and bandwidth. ACI is designed to be better than that. And that brings us to ACI's really elegant answer: ARP Gleaning. This is where the fabric stops being passive and starts actively hunting for those missing endpoints when it needs to.
So what is it exactly? Well, when the fabric gets traffic for an IP address it hasn't learned yet, it doesn't just drop it. Instead, one of the spine switches actually generates a brand new targeted ARP request. This ARP comes from the bridge domain's own gateway IP, and its whole purpose is to poke the network and say, "Hey, who has this IP address? I need to find you."
Now, this doesn't just happen by magic. For ARP Gleaning to work, you've got to have three things lined up. First, the traffic has to be IP-based, obviously. Second, you need to have unicast routing enabled on the bridge domain. And third, that same bridge domain needs a subnet configured, because that's where the gateway IP lives. You check those three boxes and you're good to go.
All right, enough theory. Let's see this thing in action. We're going to start with the most common situation you'll see: gleaning for a host that's in the same endpoint group, or EPG.
And we'll begin with the simplest setup imaginable. We've got two hosts, H1 and H2. They're plugged into the exact same leaf switch, and they're in the same VLAN. Easy peasy. Okay, so take a look at this diagram. H1 wants to talk to H2. It knows the IP, but it doesn't have the MAC address. So what does it do? It sends a broadcast ARP. But here's the kicker. Look at the bridge domain configuration. ARP flooding is turned off. And since our host H2 has been silent, the leaf switch has no idea where it is. So we're at an impasse. The leaf can't learn, and it's not allowed to flood. This is exactly where ARP Gleaning has to save the day. So here's the play-by-play. First, H1 sends out that ARP request. The local leaf grabs it, sees it doesn't know about H2, and punts it up to a spine switch that acts as a proxy. The spine then checks its big master table of all the endpoints, which is managed by a process called COOP, and nothing. It can't find H2's IP. That's the trigger. The spine takes over, generates a brand new ARP request, and sends it out across the bridge domain. H2 finally gets this ARP, sends a reply, and boom, the fabric now knows exactly where H2 lives. Okay, that was a local connection. But what happens when things are a bit more spread out? Let's make it a little more interesting. H1 needs to talk to H3, but H3 is plugged into a completely different leaf switch somewhere else in the fabric. This picture shows that exact scenario. You've got H1 over on leaf 1, and our silent host H3 is sitting way over on leaf 2. But the important thing is they're still in the same EPG and the same bridge domain. They're just not on the same physical box. And here is the single most important thing to get from this. The logic is exactly the same. It does not matter one bit if those hosts are on the same switch or on opposite ends of the data center. The process is identical. The local leaf sends it to the spine checks its database, and the spine triggers the glean. It's a beautifully simple and scalable design. Okay, let's throw one more curveball in here. What if our hosts are in the same logical group, the same EPG and bridge domain, but they're actually using different VLAN tags on their switch ports? Well, ACI handles that without even breaking a sweat. This is where the power of ACI's policy model really shines. Check it out. H1 is using VLAN 2014, but H2 is on VLAN 2025.
Logically, they're peers. The ARP Gleaning process we just talked about works exactly the same. The spine sends out the request. When that request gets to the leaf switch where H2 lives, the leaf knows from its policy that H2 expects to see traffic with a VLAN 2025 tag, so it slaps on the right tag before sending it down the port. ACI just handles that VLAN translation automatically. It's pretty cool.
So we've seen how this works inside a single EPG. Now, let's zoom out a little. What happens if our hosts are in different EPGs, but they still live in the same bridge domain? This is a super common design, right? Like a web tier and an app tier. In this diagram, H1 and H2 are clearly in different EPGs. Maybe H1 is in a web EPG and H2 is in an app EPG. But they share the same bridge domain, which means they're in the same broadcast domain. Because the bridge domain is the boundary for this kind of traffic, that ARP request from the spine gets sent everywhere inside it. That means it's definitely going to reach H2 no matter which EPG it's a member of.
And you've probably guessed it by now, the exact same logic applies even when the hosts are on different physical switches. The main takeaway here is that ARP Gleaning is a layer 2 function. It cares about the bridge domain. All that EPG policy stuff happens separately. If that silent host is anywhere inside that bridge domain, Gleaning's going to find it.
Okay, but knowing a feature's limits is just as critical as knowing what it can do. So let's be really clear about when ARP Gleaning takes a step back and lets other processes take over.
This is it. This is the golden rule you have to remember. ARP Gleaning is a layer 2 tool designed to find unknown IPs inside the same broadcast domain. It absolutely does not and cannot cross from one bridge domain to another. This slide shows the classic scenario perfectly. H1 and H2 are not only in different EPGs, but they're in totally separate bridge domains, each with its own subnet. This means any communication between them has to be routed. It's no longer a switching operation. And when traffic has to be routed, the whole game changes. The source host, H1, isn't going to send an ARP for the final destination, H2. That's not how routing works. Instead, it's going to send an ARP for its default gateway, which is the gateway IP of its own bridge domain. Since H1 is ARPing for a known address, its own gateway, the fabric doesn't see a request for an unknown IP. The trigger for ARP Gleaning just never gets pulled. It's a completely different traffic flow.
So let's wrap this up. We've seen that ARP Gleaning is ACI's smart, efficient way to find those silent hosts without resorting to noisy, inefficient flooding. It's a fundamental process that keeps the fabric running clean. So the question I want to leave you with is this. Now that you understand this mechanism under the hood, how might that change the way you design your bridge domains, or how you tackle a weird connectivity problem next time you see one in your fabric?